Audio is
Oh, I
posted.
see it.
Yeah. Got it.
Is it okay now?
Yes, it is. It is. Yeah.
Okay, thank you. All right. So when we so when we talk of a partial derivative on top of a partial derivative, there are a variety of partial derivatives that you can think of, because if you take dou f by dou x, then the second order derivative can be calculated with respect to x, which is what this thing is all about. You're calculating, so this is a partial derivative, and you're calculating another partial derivative on top of that with respect to x, or you can calculate with respect to y. Likewise, if you have calculated a partial derivative with respect to y, you have two options. Your second order derivative can be on the basis of x. It can also be on the basis of y, or rather with respect to y. So let me ask a question. If this were to be a function with three variables, let's say x, y, z, then how many second order partial derivatives are possible? Okay, I don't want the usual suspects to answer. Want somebody new to answer this question. Not the usual suspects. Seems like just the usual suspects joined the call, is it? Okay, anyone? You understood the question? So let's say, hypothetically, there are three variables here, x, y, z, and how many second order partial derivatives are possible?
9.
It
6.
was, okay, who said 6?
Sirisha.
Okay, why 6, Sirisha?
XX, XY, XZ, YY, YZ,
Yx,
YX. Yeah.
then zx,
XX
zy, zz, right? There are three variables, right?
XZ and ZX will be same, right? No.
But that's it. It's still, yeah, it is the same, but it is, okay. It just so turns out that the numbers, I mean, the expressions would be the same, but they are different derivatives, right?
Oh, okay. Then it is 9.
9, correct? You're absolutely right.
Yeah.
So it will be 9. So because for each first order derivative, you can have 3 second order derivatives, right? So moment you calculate dou f by dou x, you can calculate 3 different second order partial derivatives on top of that. Likewise, when you calculate dou f by dou y, you can calculate 3 different partial derivatives on top of that, second order, of course. And when you calculate dou f by dou z, you can calculate 3 different second order partial derivatives on top of that. Okay. So one alternative notation for second order partial derivative would be fxx, which means we're talking of dou square f by dou x square, then fyx, fxy, and fyy. Okay. It just so happens that if you were to ever calculate partial derivatives, it will turn out that dou square f by dou x dou y would be equal to dou square f by dou y dou x. It will just turn out to be the same expression. Okay. But that doesn't mean that they are the same partial derivatives. They're different partial derivatives, but you'll find that the expression that gets calculated would remain the same. Okay. Now, let's go to the next slide. Let's come to the world of linear approximations. Just give me a moment. Function of two variables. So let's start with what we know from the one variable world, and we'll try to expand that to the two variable world. So what does the one variable world suggest? It suggests that if you want to figure out f of x plus dx, then you compute f of x plus df. F of x is something that you know. How do you calculate df? Df is f dash of x times dx. So question, this is like a checkpoint for us. Can dx be a huge number? Anyone?
No, it should be very big.
Correct. So that's right. Dx can't be a huge number. So this approximation is applicable or reasonable only when dx is small. All right. If dx turns out to be huge, then this approximation is not applicable at all. Another checkpoint. So which series? You know,
Taylor.
yeah, Taylor. Okay, fine. That's fine. Now, so we're going to be inspired by this univariate world and we move to the bivariate world. Of course, the same thing would apply to the multivariate world too. So you could keep expanding this. So let's see what we have in the bivariate world. So imagine you're looking at the value of the function where the x coordinate, sorry, I don't want to use the word coordinate because the moment we use the word coordinate, we are reminded of geometry. Let's stay away from geometry. The value of x, the dimension is x plus dx, on the y it is y plus dy. And we say this approximates to f of xy plus the partial derivative of f with respect to x multiplied by dx plus the partial derivative of f with respect to y multiplied by dy. So it's very similar in a way, it's just that the big change is instead of f dashed of x, I mean, first thing is you split this whole df into two parts, right? This whole df gets split into two parts. The first part is you deal with x, the second part where you deal with y, all right? Now, so let's take an example and see how this linear approximation works. So we go to a spreadsheet. So here it is. We take a function. I'm calling it f x to the power of 4 plus y to the power of 4. We're moving from x equal to 3 to x equal to 2. And y again from 3 equal to 2. So basically we're doing the gradient descent algorithm step by step. So what do we have here? So you have iterations. So you have z. So questions, not z. This is actually f here. I don't want to call it. Sorry. Now, so let's say I start with x equal to 3 and y equal to 3. Anyone here? What is the starting value of f then? Just to wake you up.
162.
162. So basically 3 to the power of 4, 81. 81 plus 81, 162. So what's the partial derivative of f with respect to x? Anyone? Dou f by dou x. Just the expression is sufficient. Again, to wake you up, nothing else.
4x.
4x cubed. All right. And since the other is y to the power of 4, then dou f by dou y is again 4y cubed. I think that's quite evident. So what you have here is you have x, you have y, you have the partial derivative of x, partial derivative of y. For the sake of convenience, I'm keeping the same learning rate. Dx is negative 0.01, dy is also negative 0.01. So what are we doing here? We're basically moving from the point 3, 3 to this new point 2.99, 2.99. I'm trying to figure out what is the value of the function. So according to our presentation, what does it say? It merely says, first, of course, we need to calculate this bit. Dou f by dou x into dx plus dou f by dou y into dy. Okay. So which is what I do here. I multiply dou f by dou x into dx plus dou f by dou y into dy. Then I'm calling this column calculated f. What does it mean? It's simple. Before I say what it is, I want someone to look at that row number 5, and tell me what should be the formula to calculate L5. L5 is the cell that calculates the F, the revised F. Can someone tell me? I mean, I don't want you to answer. If nobody answers, then you can take a shot at it. And Sirisha, not you again, not Yash, someone else. My question is, there is a cell L5. Can someone tell me what's the formula to calculate L5? You see a number there, but what's the formula to calculate L5? What would that
B5
be?
plus K5.
B5 plus K5, absolutely. Which is precisely this expression, f of x comma y plus this whole partial derivative thing, correct? So Kyle Veri is right. So this column is B5 plus K5. Okay. So the reason why we calculate the actual y, somebody, again, not Kyle. What is actual y? Give me the formula. I don't want a number. Of course, the number is 159.8507776, but how do we get to that? Apart from Kyle Veri, Abhinav, Yash, and Sirisha, someone else. How do we calculate M5?
2.99 the whole power 4 plus 2.99 the whole power 4.
That's right, correct. So you have the y and the x, which has been revised. We have moved, and we're trying to compute. If we were to move along this curve, x to the power of 4 plus y to the power of 4, where would we be? So that's, Sandhya was right. It's h5 to the power of 4 plus j5 to the power of 4. And of course, I'm calculating an error in percentage terms, just to see how far we are. Run this process for 30 iterations. I'm sorry, 100 iterations. I reach from x equal to 3 to x equal to 2, y equal to 3 to y equal to 2. Don't worry about this. 2.99, 1.99. Don't worry too much. Okay, there's some minor mistake somewhere, which is why we should have actually seen 2 here. I don't know why it is 1.99, but don't worry too much about it. Not very important. So there's this error, negative 2.44. So what do we do? Okay, let's see. We try to make it a little better. Look for a better approximation. So we use the same template. Nothing changes. All that we do is we play around with the learning rate. So instead of using negative 0.01, we plug in negative 0.001. Now let's see what happens. We go all the way down. Okay, again, don't worry too much about 2 and 1.99. It's not going to be very material, but still, anyways, the error is negative 0.238%. All right. So clearly, when the learning rate is smaller, the error that we get to see is much smaller. And it's understandable because that's what the whole Taylor series is all about. It says, look, when this dx and dy is small, when it is very close to 0, you get a better approximation. When dx deviates, your approximation gets poorer and poorer. That's the whole deal behind Taylor series. Now, if you go back to our discussion on univariate calculus, and when we did approximation, in the previous session, we also discussed a scenario where we introduced the second order expression from the Taylor series. And we saw that if we introduce a second order expression from the Taylor series, the approximation gets much better. And you get, it's much closer as compared to just working with the first order approximation. So let's see if we can do something similar in the bivariate world. So let's understand this a bit. What you see on top is the univariate world. F of x plus dx approximates to f of x plus f dash of x dx plus 0.5 times f double dash of x dx squared. Typical Taylor series approximation, univariate world. Now, how would it look in the bivariate world? And of course, this would extend to multivariate as well. This is where the Hessian matrix comes into picture. So think of the Hessian matrix as a matrix of all possible second order derivatives, partial derivatives. So we talked about partial derivatives a while back. We said when you have two variables, x and y, you have four partial derivatives. Question: would Hessian matrix be a square matrix or not? Someone, not the usual suspects, not the ones who've answered today so far, someone else. Would Hessian matrix be a square matrix or not? You know what a square matrix is? It is one where the number of rows and the number of columns remain the same. Anyone apart from those who've answered today? I'm going to keep silent. I'm going to stay mum until someone answers. If you didn't understand the question, please ask.
Sindhuja has posted yes in the chat.
Sorry, say that again.
Sindhuja has posted yes in the chat.
Yes, she is right. So, give me a moment. The Hessian matrix is a square matrix because it's evident here because the number of rows is equal to the number of columns. Had it been three variables, then we'd have had 9 partial second order derivatives. And you would find that again, the Hessian matrix is a square matrix. So what are we going to do now? So we're going to have our own little expression for the Taylor series in 2 variables. And we're going to go to the second order expression. So let's see how it looks. So the way to, one way to think about it is, so here's the univariate expression. Okay. Now we're moving to the bivariate one. So you basically replace f double dash of x with h of x comma y, the Hessian matrix, 2, 2 matrix. And just imagine this dx squared to be split as dx here and dx here. Okay, just imagine. And since we have 2 variables, think of a vector or a matrix dx and dy. On the other side, think of dx dy transpose. All right, so that's the way to write this expression, the second order expression for Taylor series when you have 2 variables. Now, of course, we need to expand this. It's not too complex, folks. It's simple. All that you have to do is just plug in the matrix here and do simple matrix multiplication. Just make sure that you multiply. Okay, before I ask, before we proceed, someone. So let's say I'm multiplying this matrix by the Hessian matrix. Once I multiply the 2, can somebody tell me what would be the dimension of the product of these 2 matrices?
One by two, easy.
1 by 2. That's right. Correct. So you have a 1 by 2. So basically the idea is this is 1 cross 2 multiplied by 2 cross 2. So the product of these 2 matrices would be 1 cross 2. And I have so which means I have a 1 cross 2 matrix here. And if I multiply it by this, what would I get? Someone. I have a 1 cross 1. That's right. Why? It's 1 cross 2 here. This is 2 cross 1 because don't forget, I'm doing a transpose here. So which means dy comes below dx, right? So what I'll get is 1 cross 1, which is a scalar, right? 1 cross 1, of course, we know it's a scalar. You put only one element there. Now that is this expression. So if you multiply this, this is what you'll get. 0.5 times this is the second derivative fxx multiplied by dx square, and then 0.5 times fyy multiplied by dy square plus 0.5 times fxy dx dy plus 0.5 times fyx dy dx. Now, what we do is, as I said before, fxy is same as fyx. So which means I can treat this as fxy. So which means I can do a simple summation of these two expressions and I'll get fxy multiplied by dx multiplied by dy. So here is the second order expression for Taylor series when you use two variables. Okay, so let's go back to the Excel and let's see what's happening when you do bivariate. So I'm going to ask a bunch of questions now. So here's the function, the same function, x to the power of 4 plus y to the power of 4. Someone, what's the second derivative of f with respect to x? Anybody? This time it's open to all. It's 12x squared. All right. And of course, second derivative of y with respect to, f with respect to y, be 12y squared. Anyone? What is dou f? Dou square f by dou x dou y. Dou square f by dou x dou y, or fxy. Fxy. That's another way to refer to that. Second order derivative, 0. That's right. Why 0? Who was that? Was that 0?
I will see. Because if you take dou x dou y, dou f by dou y will be having in terms of y only. Again, if we take derivative of x, then it is considered as a constant, so it's 0.
That's right, correct. So she's right. So if you look at this, the first order derivative of dou f with respect to x has only x terms. Likewise, the first order derivative of partial derivative, of course, of f with respect to y only has y terms. So if you look at the second order one, where if you talk of dou square f by dou x dou y, then of course it'll be 0 because there are no y's in the expression. And likewise, dou square f by dou x dou y would also be equal to 0. So now, once we have these nice looking expressions with us, I'm still calling it nice. I'm doing exactly the same thing. Nothing changes. It's just that this, we all remember this number, negative 2.16. It comes from here. So if you go to this number, I have my second order calculation. No rocket science there. It's just doing this calculation here. Whatever you get to see. Then I have my calculated f, which is nothing but. Okay, now I want somebody to answer. So when I'm calculating P5, what am I going to sum? Just to wake people up. P5 would be the sum of which two cells? Briefly, This is this expression, that's K phi. You have a bunch of derivatives calculated at this point. Which point? Basically this point. And there's a second order calculation, which is nothing but this whole expression is calculated in O5. My question is, what is P5? It's a sum of which two cells? Anyone? Open to all.
K5 and O5.
Okay, that's right, correct. It is K5 and O5. Why? Because this is, of course, we know that this bit is from the first order. I've done the second order calculation. So we know according to, say, Taylor series, we sum up the first order calculation and the second order calculation. So she's right. Oh, wait a minute. Why am I seeing a B5 here? Wait. Oh, okay. Sorry. K5 plus B5 plus, of course, the original, the initial value, right? So that's there. Because if you look at the expression, it's fxy plus this whole thing plus this whole expression. So which is why you see three cells being summed up here. Okay, I don't think that should be a problem. Most all of you should understand that. And then of course we calculate actual y. So what do we have when we go down when it comes to the error? Here we go. It's negative 0.01. That's the error. If you look at the dx that we've been using, it's only negative 0.01. I'm not using a small dx and dy, and yet, and if you look at the error, it's negative 0.012%. Let's compare it with what we have in the first order world. Here, this was negative 2.44. And even when we had dx and dy as negative 0.001 and we did 1,000 steps, right? Let's look at what we have here. It's negative 0.23. Look at the difference, folks. Negative 0.01 and negative 0.23. Right? That's the difference. Now you might think, what's the big deal? I can tell you, millions are made in the financial world on the basis of this difference. And I'm not joking when I say that. So in the world of finance, the second order derivatives are used extensively. And if we don't use the second order derivative, then banks, the big banks of the world might end up losing millions of dollars. So it might seem to be trivial, but it isn't. It's huge. Okay. So any questions so far before we proceed? None? As always, I shall take silence as no questions. So let me proceed. So the final bit that we're going to talk about is chain rule. So this takes us back to the univariate world where we understood chain rule. We're just extending the chain rule that we learned in the univariate world to the multivariate world. Of course, we're going to work with two variables. You can certainly work with more, but I think two is sufficient for us to build the intuition, for us to extend to higher order, more variables. So we're going to look at two cases, okay? Chain rule with one independent variable and chain rule with two independent variables. Anyone here, what is an independent variable? Open to all.
It's not dependent on anyone. You can take.
All right.
any
So
variable.
in the machine learning world, what do we call
Features.
That's right, features. So that's the term that we use in the machine learning world. So in this case, just forget the graph below. Can you just tell me which one? Not Sirisha, not, I think it was Sanjay who answered. Which one is the independent variable? Just read this whole sentence.
T,
Sorry, say that again.
T.
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 That's right, correct. Because you can play around with T. So the way, if you look at the way these functions work, don't worry too much about differentiable and all that. Such terms would kind of get you off track, but it's important in a math book because math books always want the definitions to be complete. Okay, so don't worry too much about stuff such as differentiable functions and things like that. So don't worry about that, but let's just focus on what is the gist of what's going behind the scenes here.
Actually,
So
this equation looks very familiar with some physics equation, I guess.
It's supposed to be used extensively in engineering. Okay, so I believe it should be, anybody who's done engineering should find this familiar, of course, at least for the first few years after graduating. Of course, later most people forget. Anyway, so let's look at this. So what are we saying here? So here is a variable T, of course, an independent variable. So we can call that feature in our world. And we're talking of continuous functions here, so which means T can, vary. So when I say vary, it can take continuous numbers, continuous values. Okay. So here's a function G, and you get X. Another function H, you get a Y. X and Y feed into another function, and you get Z. All right. So Z is essentially nothing but f of x comma y, or you can say Z is f of x t comma yt. Okay. So now the question is, why the hell are we doing all this? You just imagine, folks. So typically in the world of neural networks, you'll have multiple layers. So you have one layer and you have a set of functions, that produce an output that feeds into another layer. That in turn will feed into another layer, so on and so forth. Okay. So very common in the neural networks world, or rather in the deep learning world. So that's one area where we will be using chain rules extensively. Okay. Now, setting that aside, coming to the mathematics. So the way to differentiate this, of course, we're not going to get into the derivation. That's not the objective here. That's pointless. We're not here to learn that kind of mathematics. But let's try to understand, if I have to do this partial derivative of Z with respect to T, for instance, how do I do it? Okay. So here is how you do it. So what you do is take a function, Z is equal to f of x comma y. You calculate, so Z comprises of, there are two variables that go into Z. So calculate the partial derivative of Z with respect to X, Z with respect to Y. And then you know that X is also a function of T. You know that. So here, question, why dx by dt? Why not dou x by dou t? If you look at this, they're calculating dx by dt. I don't see a dou x by dou t. Why? Think, folks, when do we use dou's? Why am I seeing a dou z by dou z by dou x, but not a dou x by dou t here?
Univariate.
Exactly, it's univariate. You see that? Look at this, folks. X is g of t, that's it. Right? It's just one variable there. So you don't need a dou, which is why you don't see a dou. It's as simple as that. Correct? So what are we doing here? Let's understand this branch clearly. You start here. There are two branches, evidently. Why? Because there are two variables feeding into Z. One branch is dou Z by dou X, the other branch is dou Z by dou Y. Now you're dealing with X. We know that X is a univariate function of T. So what do? Simple dx by dt. So this whole branch, you just multiply these derivatives, dou Z by dou X by dou T. That's one branch. Let's do the other branch. So here you pick this variable Y. So this is dou Z by dou Y. But we know now Y is a function of T, H of T, of course, right? So what do? You calculate Y with respect to, you calculate the derivative of Y with respect to T. And if you look at this branch alone, what are you going to get? Dou Z by dou Y multiplied by dy by dt. The arguments are the same. Why dy by dt? Because Y is a univariate function of T, which is why it's dy by dt, not dou Y by dou T. All right. So eventually you just sum up these two expressions. So which is what you see here, and that's your dz by dt. Okay. Again, question. Why dz by dt? Why not dou z by dou t?
Z is a function of both X and Y.
Okay. So why dz by dt?
So we are finding Z with respect to T.
Correct. It's just with respect to t. Had this been z with respect to, say, ABC, then you would have done dou z by dou A, dou z by dou B, dou z by dou C. Right? Here there is only one independent variable. So in a way, even though this is like a complex function, effectively this is like a univariate function between T and Z. You see, it takes a circuitous route, but effectively it becomes a univariate function. So I'm jumping the gun here. Let's not use terms such as univariate here, but that's one way to look at it. Okay. Now let's do the next one. Here, what we have is we have two independent variables, U and V. Okay. Again, in the neural networks world, imagine a neural network node, and you get two inputs into that node, producing an output. Right? That's one way to look at X is equal to G, of a function of U and V. That's one way to look at it. Right? So U and V, of course, are independent variables. You have two functions, X equal to G of UV, Y equal to H of UV. And of course, you have a Z, which is a function of XY. Okay. Now, so let's get started. Let's look at all possibilities here. So you start here. Like always, you start here. Okay, you see Z equal to f of x comma y. So let's start with a simple derivative. Okay. Dou Z by dou x. So this is no different from what we saw here. You see here, dou Z by dou x, dou Z by dou y. Right? Dou Z by dou x, dou Z by dou y. No difference at all. Next, you come to x. Now you see that x is a function of u comma v. You see that? Of course we do. So which means, don't you see, I can split this into two partial derivatives. Why? Because x is a function of u and v. So I'll split that into dou x by dou u, dou x by dou v. All right. So there are how many branches here? You see, I come here, then it splits into two branches. So don't you see that I have dou x by dou x multiplied by, dou z by dou x multiplied by dou x by dou u. That's this. Dou z by dou x multiplied by dou x by dou v, which is this. So let's come to the bottom part of the tree. This bit, again, is same as what we saw here. No difference. But then again, we know y is a function of u and v. So I can now differentiate y with respect to u, partially differentiate, of course. I can also partially differentiate y with respect to v. So just as we did, just as the math that we did at the top part of the tree, we exactly do something similar here, and this is what we get. Okay. Now the point here is, if you look at it, just read this. What are we trying to figure out here? We're trying to figure out the chain rule. So when we're figuring out chain rules here, remember, we are trying to figure out the derivative of z with respect to what? Which variables? Anyone? Abhinav, not you. Someone else.
U and V.
U and V. That is right. Correct? So now is it a dz by du or a dou z by a dou u?
Dou
Z
Z.
for dou u because it's multivariate.
That's right. Correct. It's multivariate. Correct? So we are calculating a dou z by dou u and of course dou z by dou v. So how do you calculate dou z by dou u? It's very, very simple. Look at this. Think of this as a bunch of final expressions that you're going to mix and match. Some of them will go into the dou z by dou u calculation. Some of them will go into the dou z by dou v calculation. All right. So it's very simple, folks. Look at this. Dou z by dou u is this expression, which is nothing but this. And then plus this expression, which is nothing but this. So effectively what you're doing is, you have 4 expressions here. Look for the ones where you see a dou u, club that into this. Look for the ones where you see a dou v, club them into this. All right. So you have 2 expressions, one for dou z by dou u, another one for dou z by dou v. Okay. I'm not doing any examples here, but let me stop here for any questions. Nothing at all? All right. So that ends calculus. So there is one concept that we haven't talked about, which is the Jacobians. To be honest, I haven't gone through too much on Jacobians. I think we would need it when we do deep learning. Let's do it when we get to that stage. All right. So I don't want to saddle this audience with more calculus terminology. So I thought let's park Jacobians aside, but this broadly covers the calculus that we would need for, at least the basics of calculus that we would need for machine learning. I'll stop here for any questions. Are there any?
Yes, please.
Go ahead.
Can you go to that Excel?
Sure.
I don't understand the many terms there.
Yeah,
This
please.
one, can you repeat it?
Okay. Which one? Do you want to look at the bivariate first order or the second order? There are 2
The
tabs
second,
here.
second order.
All right, second order.
Yeah.
All right, so let's understand this. So what are we doing here? So basically, just give me a moment, folks. Just getting a call. Just give me a moment. Okay. Sorry, I'm back. All right. So what we're doing here is we are trying to figure out this in a way. If you go back to the presentation. So do you understand this bit? F of xy plus dou f by dou x into dx plus dou f by dou y into dy. Do you understand that bit, Sanjay?
Can you please repeat this too?
All right. Okay, it's simple. So what we're saying here is, you understand the univariate
Yeah.
right?
Yeah.
So when it comes to the bivariate and first order Taylor series, okay, we're still talking of first order.
Yeah.
We haven't gone to the second order.
Okay.
So when it comes to the first order, all that we're doing is I'm taking the univariate expression as my inspiration, all right? And I'm kind of playing with that. So how am I playing with it? I'm replacing f of x by f of xy because it's bivariate, right?
Okay.
Of course, LHS is, I'm trying to figure out f of x plus dx plus y plus dy, correct? That's evident.
Yeah.
Now, the df in the univariate world is f dashed of x times dx, right? That's
Yeah.
how it was in the univariate world. Now, the bivariate world, I'm replacing this with two expressions. Why? Because it's bivariate, right? We know what is f dashed of x. F dashed of x is the first derivative of f with respect to x, correct? So here, all that we're doing is we are replacing this with two
Yes.
expressions, all right? Dou f by dou x into dx plus dou f by dou y into dy. Is that clear? Sanjay? I can't hear you.
Why there is dot one?
Sorry, say that again. I didn't understand.
Why there is dot derivative and there is star?
No, you're not audible. Say that again.
No, he's asking why there is dot in one and
Dot and
and-
star.
Oh no, it's the same thing. It's the same thing. Don't worry. It's my mistake. So don't give too much credence to the star. The star and the dot are the same here. It's multiplication. So don't really worry about it.
Okay.
All right. But apart from that, does this look clear? Any questions on this?
Yeah. Yes.
All right. Do you understand this bit, the Hessian bit? Sanjay. We can't hear you, Sanjay. Is he typing something? Let's see.
No, I think
Yeah.
he lost. I mean, we lost him. He's not there now.
We lost him?
Yeah, we lost.
All right. Okay. Okay. Anyone else apart from Sanjay who has any questions so far?
VC, I do have a question.
Yep. Sabarish.
Yes, VC. So my understanding is that, when we go for second order derivative, the accuracy increases, right?
That is right.
So proceeding further, so if we are moving to the third order derivative, so the accuracy will be like keep on improving, right?
That is right.
That's my understanding.
Correct.
Okay, right. So
But
if I
it
have
comes at a cost. It comes at a cost, computational cost, right?
okay,
So you
VC, got
weigh
it.
the computational cost vis-a-vis the gains that you make. So
Okay, VC.
what we have seen is even in the financial world, I talked about making or rather losing out millions, right? Even in the financial world where every cent matters, they stop with the second order. That's sufficient. It's a very good approximation. All right.
Okay, VC, got it.
So usually this, which is why we stop with Hessians. We don't go beyond Hessians.
Okay, VC, got it.
Which means we can say higher the order is indirectly proportional to the rate of change of the dx, how quick the dx changes or how large it changes.
Say that again.
Let's say increasing the order will decrease the rate of change. Is that right?
You can achieve. No, when we say decrease the rate of change, yes, you can say that. So it's like this. So if I take let's do this. Let's work with a single order. I mean, the single univariate one.
Mm-hmm.
First derivative I reach here. right?
Mhm.
Second derivative, I may reach, I mean, second order, I may
Mhm.
reach here, very close to this point.
Mhm.
Okay, it's a pretty big leap. If you look at the first one, it's a giant leap. I move so much,
Mhm.
right? Then I might move a little bit here. If I run this, I mean, if I go to the second partial derivative, if I go to the
Mhm.
third, a little bit more, so on and so forth. Which is why, if you look at this expression as well, you can see that. Look at this. It's dx squared,
Square. Yeah.
right?
Exactly.
So if you go to the Taylor series and you go to the next expression in the Taylor series, you'll find a dx cube.
Mhm.
So you would find with every additional derivative that you take, yes, you go closer, but it's like an asymptotic function there where you go
Mm.
closer and closer, but you're not making too much progress. You're just making a little progress. And with every step, the progress is much less compared to the previous step, right? So which is why we generally tend to stop with the second order derivative. We don't go to the third order, though theoretically you can go to third, fourth, fifth, infinite, in
Mhm.
fact.
Okay, because I've tried to replicate what you have did visually. You have shown us the sheet, right? So I was trying to visually replicate it, like see the difference between like different orders and different learning rate, all those stuff.
Okay. Did you
So
try?
yeah, I made a chart where you can zoom in and actually see what is the error rate between there.
You have it handy?
I'll yeah, but okay.
Maybe next time share it with the group,
Yeah.
right?
Yeah, I have it handy, but yeah, next time I'll do it because I'll make it more
Yeah, that'll be
aesthetic.
fun.
So
Yeah, these are the kind of fun stuff that folks, you can try. That's the only way to learn. I'm doing the Excel way because Excel is I'm comfortable with Excel.
mm,
You can do the same thing in Python and draw charts and then figure out what happens, right?
yeah, so I've tried that. Yeah, I haven't gone for a second order thing. What I've given is you can give any equation as an input to that as a string, and you can choose from where you have to come where, like the start point and end point.
So
Uh,
you automatically calculate the derivative, is that right?
yeah.
So using SymPy?
Yeah.
All right.
Yes.
Okay. All right. So folks, SymPy, again, I think I don't want to talk about it. You do another session on how you can use SymPy to calculate derivatives, and then
Sure.
right, that'll be fun.
Okay.
Anything else?
We see one more thing like as for now what we have discussed, to simplify thing maybe in a one or two line, let's say calculus is nothing but like we are going to see how small like if you need to approximate certain thing, we have to let's say uh do an like we have to see how the equation changes to the smaller extents, and you have to traverse along the way. Increasing the order will decrease the rate of change, which means it will be minimal.
That's right.
So is that like sorry, like I couldn't make it in a one sentence. Let's say, are these two the key? Maybe like aren't we missing something, or
No, that
you want to
is
summarize
from
it in one or
from an intuition standpoint, I agree. All right.
okay.
Of course, the math is a bit more involved, but from an intuition standpoint, yes, I do agree.
Got you. And let's say like I really need to see, right? So I can understand increasing the order will decrease the rate of change, but how do I prove it mathematically? Like, do you have any derivations for this telling that okay, this is where it is? Using common
Okay,
sense, yes,
no,
I can get
I
that.
think about. Okay, look at it this way. It's okay. Let's do this. Since you're saying this, you remember we learned about geometric progression, right? So here is x squared, and x cubed, right? So don't you see if x is less than 1.
Yep.
Or greater than -1. So basically the modulus of x lies between 0 to 1, the modulus, right?
Mhm.
Don't you see that when I'm dividing these two expressions, then this would bring this down by, so let's say if x were to be 0.01, say 0.01 here. And this of course is 0.0001, correct?
Yeah.
Am I wrong here? No, I'm right. Okay.
Point. Yeah.
Then
Correct.
this is, or let me make it simple, 0.1, 0.01.
0.001.
So don't you see that with every progressive step, I'm coming, I'm bringing this down by a factor of 0.1, isn't it? So don't you
Yeah.
see that if I make some progress here, so let's say this whole expression is, I'm multiplying it by number 10 throughout, okay? So don't you see that if x were to be a value between -1 to 1, then we know that this, this value would of course be less than this, and this value would be less than this, correct?
Yeah.
So
Yeah.
you multiply this by any constant. I'm just taking a constant here to make it easy. Then if I multiply these two, 10 multiplied by 0.1 is 1, see this?
Yeah.
It will be lesser, right? So it's like
Yeah.
if I move by 1 unit in the first order world, then I'll move by 0.1 unit in the second order world, right? But then I'm assuming that this is the same. But in fact, if you go to Taylor series, if you look at the Taylor series expression, in fact, you'll find that this is, even this factor is less, right? It's 0.5.
Yeah.
If you go to the, wait a minute, let's just Google for the Taylor series. So you bring it up. Taylor series, unique variant. See if this helps. Confusing. Wait, let's see this.
I think you can check out the images tab.
This is okay, not too bad.
Okay.
Look at this. The denominator is a factorial. You see that?
Yeah.
F dashed of x by 1 factorial, 2 factorial, which is why it's 0.5, then 3 factorial, 4 factorial. So in fact, what actually happens is, this is not even a constant that you're dealing with. It's much worse. This is 1 factorial, right? So this is actually factorial. I mean, that's again 1 by, I think we have a factorial. Wait a minute. Fact is there. 1 divided by fact of 1. And this is 1 divided by fact of 2. And this is 1 divided by fact of 3. You see, it's much worse. You see why? Already we're dealing with an x which is very small, which means with every progressive step, we're dealing with a smaller and smaller. That's already small. On top of which, you have a factorial in the denominator. So it's like compounding the problem in a way. So it's like, look, I multiply these two, it's 0.1. Now I'm already dealing with a smaller number with respect to x squared, but then this number is much smaller again compared to 1. This is much worse, so on and so forth. So if you go to the 100th expression, you're going to deal with something like 1 by fact of 100, which will almost be 0. You see, this is 0, literally, right? So you can see, you might end up seeing an exponential drop, literally, right? Close to an exponential drop.
Okay, yeah, makes sense. Let's say if you want to move from 3 to 2, on X it will be around 10, on Y it will be around, let's say, 2000. Like square it will be 2000 and so on. So the computation for X cube is sky.
Correct. Right.
Got you. Awesome.
Anything else, folks? All right. If there isn't anything else, we wanted to do decision trees today, at least an introduction. Sirisha, just a 5-minute introduction. Let's not get into the details, but let's just talk about what a decision tree is, what sort of problems we solve with decision trees, and then of course in the next session we'll get into an algorithm and then explain to the audience
Okay.
a typical decision tree algorithm. So I leave the floor to you now. You can share your screen. I'll stop sharing. Just the first few slides that you have, that's sufficient. Let's not get into algorithms. Let's just briefly. Yeah. Now, can you show us one decision tree as an example so that people can just open one decision tree that you have? No. Side by side, so that go to the top. Start with the go through the presentation that you have, but just show us a decision tree so that people can relate
ma'am.
to. Okay.
Okay. This one we see.
Yeah, this is good. This is good.
Okay. So I want to start with the basics of decision tree. Okay. Decision tree, I mean, it's nothing but it's just like a conditional branching. We know, right? If this is satisfied, this should happen. This is satisfied, that should happen. It is something like that. So decision tree is a similar kind of structure. Okay. There we make decisions at which we call as nodes. I'll explain what is nodes and all. At a high level, this is a tree-like structure where we have different decisions or different outputs. For example, if you see this, right, this is one such example.
Now, what is the big picture problem statement when it comes to that example? Can you show me what decision are we trying to take there?
Here we are the decision is if a person will play or not, based on this condition.
Play what?
Play what is that?
Tennis.
Yeah.
So can you just take us through one branch here?
Yeah. So if you see this, right, I mean, we have actually different features. Let me show you.
No. Forget features now. We'll come to that. But can you
okay.
Just help us go through the branch so that I can.
Okay. So if you see this, right, I mean, we have different features here where outlook is nothing but what the climate is, if it is sunny or rainy or overcast. Okay. And inside sunny also we have humidity, and overcast and rainy. Under rainy outlook we have something like windy, and under windy, like if it is a strong wind or a weak wind. I mean, depending on all these factors, right?
Question, Sirisha, under rainy outlook.
Outlook under.
No, they're independent, right? Rainy has nothing to do with windy, right? So what are the features here?
Features are outlook, humidity, windy.
Okay,
these are features, and these are all like the values actually. these branches
Take
are
me
nothing but
through one branch. Take me through
Okay.
one branch and help me understand how to interpret this decision tree.
Can I
Just
show
take
this
this. Just
data?
don't go through the data. Just show us the decision tree.
Okay.
It's important for us to understand. Okay.
Okay.
Just take us through one branch.
Okay. So if you see this, right, these are nothing but nodes. Nodes are nothing but features. Okay. In a decision tree, we have all the features at the nodes. So Outlook is one such node, or this is the root node. Okay. The Outlook has a different outputs. Something like Outlook, I mean, it can be windy or sunny or rainy, like whatever the climate is.
Let's be very careful here. In this case, will Outlook be windy?
No.
No. Windy is a feature in itself. So
Yeah.
what values do Outlook take?
Here it takes, like in this problem statement, it takes only these three: sunny, overcast, and rainy.
Okay. So let's say the Outlook is rainy. Then go down that branch. What are we doing then?
So here, if it is rainy, right? Okay. So after that, we have something called, we have other features too. Okay. Like for this problem statement, let's say we have some 5 to 6 different features, out of which I have taken one more feature, which is nothing but windy. Wind is nothing but wind, the type of wind outside. If it is a strong wind or a weak wind. Okay. Wind again has two outputs. One is weak and the other one is strong. See, if it is very strong wind, you cannot play tennis, right? Your cock will not go. So this is no. If it is weak, yes, you still prefer to play. So that is where you have yes.
Okay, question. So we keep talking of attribute values pairs, right? So what is the attribute? What is the value? Yeah. Which one is the attribute?
Attribute are nothing but features.
Okay.
Outlook,
And values?
humidity, windy are the attributes or the features. Values are rainy, weak, strong. I mean, what happens is in decision tree, right? It is like it has predefined. I mean, it's not like what do we call, like many values or like continuous variables. It will not be many. Like you will have predefined values, something like weak and strong, or rainy and sunny.
No, okay. Let me qualify that. You can also do continuous by bucketing it. Okay.
Yes.
There is a
yes.
possibility. We'll discuss that sometime later. But yes, broadly, each attribute will have a certain set of
predefined
values.
set of values. Yeah.
Okay. Now, question. So when I traverse this tree, Outlook is equal to rainy, windy is equal to strong, then no, which means I don't play tennis. Correct?
Correct.
I see two conditions here. Outlook is equal to rainy, windy is equal to strong. Now, when I combine them together, do I use a logical AND or do I use a logical OR here?
This is logical AND.
All right. Okay.
Yeah.
So which means when you traverse down the tree, we're using a logical AND condition, right? Okay.
Correct.
Thank you. Now go back to the original presentation. Thank you.
Okay.
Go all the way to the top.
So basically, that is a decision tree. Now, I want to explain like the problems which we can solve.
No. Just explain this again. Yeah, explain this. Yeah, go ahead. Yeah.
Okay. What is decision tree? Okay. So decision tree is nothing but it's a trees of decisions. Okay. I mean, it is like condition. It is just like conditional branching. I mean, we can come similar to conditional branching, where if this condition is satisfied, this should happen. The other condition is satisfied, this should happen. Else something else should happen. That is how we know if else thing, right? It is similar to that. So it is nothing but decisions of trees where we can go through specific branch and say that, okay, this will happen. For example, like as VC has already highlighted, right? Yes, if it is rainy and if it is a weak wind, yes, a person can play. If it is rainy and if it is strong wind, no, person cannot play. It is something like that. These are all decisions at each level. This is nothing but a decision tree. Now, I want to explain the problems, like the places where we can use this decision tree. Okay. Now, for example, let's say if the instances are represented by, like as I already said, right, fixed pair of attributes pairs, something like, if you see this, right, or let me show you the data set. That will be easy. Yeah. If you see this, right, see, any feature if you take here, outlook, temperature, humidity, windy, these are all features. Features are independent variables. And play tennis is there, right? This is a dependent variable or the target. Okay. If you see any of the independent variables, right, it is taking only very few set of values or predefined values. Something like, if you see outlook, it is like sunny, overcast,
Okay,
rainy.
so what is the terminology? Bhargav taught us that for such variables.
Mm,
Would you recollect? Anyone on the call? Not, of course, not Naveen, but not the
Categorical.
categorical, right? So these are categorical variables, right?
Okay.
Go ahead.
So,
But again, folks, from what I hear, you can do decision trees even on
continuous variables.
yes, you can, by bucketing it into various, groups. So it's like 10 to 20 is one group, 20 to 30 another group, that sort of thing. But let's not worry about it. For all practical purposes, let's assume that we work with categorical variables. Go ahead.
Yeah. Now, if you see also, like, it has only 3 different values, right? It will take any of these 3 only. I mean, it's not limited to 3. Okay. I'm just, for example, like for our understanding purpose, I'm just explaining this. And temperature, if you see this, right, these are our specific values here. So, I mean, in this case, I mean, if we have this type of conditions, then we can go with decision learning algorithm. The other one is the output has discrete output values. Something like, if you see here, like we have yes or no, true or false. So in this case also, we can apply decision tree. And the other one is, whenever, right, I mean, when we collect the data, okay, there are chances that we may capture few errors also. So in that case, I mean, also we can go with a decision tree, because this is, I mean, very robust to errors. Okay, which means, like, even if there are certain errors, I mean, training errors, right, this will give accurate result. Okay. And in some cases, right, I mean, we may miss few values, like while taking that, I mean, while taking the information, right, we may miss few values. So even in that case, right, we can use decision tree, because this has the feasibility where, I mean, the algorithm has different features where if there are no attributes, right, we can, I mean, actually cut it. I mean, we can get the value basing on the parent node of it. Okay, that is how this algorithm is designed. Okay, because of which, in these conditions, I mean, wherever these conditions are satisfied, right, we can definitely go with decision tree.
All right, so
Now,
let's not get into the details. Okay, so just a brief overview of what a decision tree is. So we'll discuss the details in the next session. Any questions so far, folks, on what a decision tree is? All right, if there isn't anything else, let's stop for the day, and we shall catch up again on Wednesday. Thank you, folks.
Good night.
Yeah, bye.
thank you. Bye.
Thank you. Thank you all.